those of you that have been reading the messages and keeping up with our reports and our discussions, certainly one of the many things we care about in this new world is vortex ring state and how that's new and different for these eVTOL type aircraft. It's pretty mature when it comes to classic helicopters and reasonably mature when it comes to V-22 type aircraft. There's certainly been some lessons learned and so forth. And the big question is, all right, what can we take from that and apply to the VTOL world? And of course, our concerns are obviously safety, but there's also performance and so forth. And how do we establish operating limits so that we can be safe? And so with that short introduction, and if you recall last fall, we spoke about Richard Brown's paper, and we put it in our library and asked everybody to pre-read it. So hopefully those of you who have pre-read it will have especially good questions. I will defer at this point to Richard, if you want to tell us how you want to run this, if you want to just talk uninterrupted, or if you want to have a play-by-play and have open mic for all this, whatever you like is fine with us.
Can you hear me still? Good. Well, okay. First of all, thank you very much for inviting. I think it's a great honor to present this talk to such an esteemed audience. I'm expecting to learn an awful lot more than I'm going to teach you, I think, given who you actually are. I noticed a few familiar faces amongst the audience, so hello to those as well, and hopefully afterwards we can have a good discussion. I don't mind how we run this. The presentation as it stands has been given in anything from 35 to 45 minutes. So either we can run straight through that, or I don't mind being interrupted as we go on. And if anybody has any burning questions, then please feel free to chip in. We'll see how the logistics of intercontinental internet goes. If I disappear or if I ignore you, it's probably more to do with electronics than me. So let's try and deal with that as it emerges.
That's fine. And as you're doing that, I'll keep an eye on the chat, and okay. I can field questions and kind of throw them in.
All right, that's probably the best way of proceeding now. Yeah. Okay, so as the next trick, I will try to present my screen. And hopefully you can start to see this.
Yeah, looks good.
Did you actually see that as a presentation?
Yes. Well, yeah.
Okay. Let me try from that. Can you see the whole presentation, the whole screen?
Yes, you can see the whole screen.
Excellent. Okay. So this is a talk that I've given in two different versions before. The first time I gave it was at the European Rotorcraft Forum in Switzerland last year in September. And then what I did is I added a little extra work to make it a little bit more appealing to regulators, and presented that in Cologne at the EASA Rotorcraft Forum in November last year. So what I'll do is I'll present the version of the paper that I gave in Cologne, which does have that extra work on vertiport design stuck in it there. If you've read the paper online, unfortunately the paper doesn't go as far as including that, but I'll try and make amends for that by explaining what I did in some detail. Okay, so let's go back into history. Where I tend to like to start this talk is on the 18th of April 2000. With that terrible accident in Marana, Arizona, when a set of 3 US Marines V-22 Ospreys was flying in formation, practicing a tactical descent at night, going into a landing site in the desert. And what seems to have happened is, as quite commonly does happen in these cases, is the first helicopter, the pilot thought he was overshooting the landing site, pulled into a steeper descent, and upset the pilot in the aircraft behind him. And what happened in that particular case is the pilot behind him increased his descent rate, and within a few seconds was upside down and crashed into the desert, killing the 19 folk, all 19 folk who were on board that particular aircraft. Now, what that heralded was the re-emergence of a problem which had largely kind of been sidelined, if you like, in the helicopter world per se. It's not that vortex ring state wasn't unknown. You go back into the history of vortex ring, and there was quite a bit of academic research on that basis. if you spoke to the old pilots who'd been in Vietnam or had been in the British situation in the Far East, they'd all encountered vortex rings in some fashion or other. But it was always thought to be a fairly sort of marginal case that some folk would experience and some folk wouldn't. And what had really happened is with this large, very heavy aircraft with somewhat different design characteristics than those that had been experienced, and all of a sudden this vortex ring state came to the fore again and was implicated in this particular accident. And of course, as you know from the history, that led to a huge polemic, and on the positive side, to a lot better understanding of what vortex ring state actually was and what caused it. So just by way of a little bit of background, let's talk in various ways. First of all, let's consider, if I can get my mouse back, let's consider some aspects of the vortex ring state. Let's have a look at the rotor wake. And since those days, our understanding of how rotor wakes behave has increased immeasurably. We've now got very high resolution computational techniques which can go ahead and visualize what's going on in detail. And there are also some experimental techniques which have shed an enormous amount of light on what actually goes on in the rotor wake. So what I've drawn on the right-hand side here is one of our results. It's a computation of a rotor flying along in level flight under normal operating conditions, if you like. And the pertinent characteristics to point out here is, here's the rotor. You can just see vestiges of the rotor blade sitting in here, and the rotor creates this tubular vortex structure below it. But now, if you go to the classic textbooks, that's where the story ends. But what's really going on is that tubular wake is inherently unstable. And so as you go down into the wake below the rotor system, what you find is that instability tends to break up this tubular structure until behind the rotor system, you end up with this smash of fragmented vortex elements, if you want to call it that. Now, this is on the left here is the situation with the rotor in vortex ring state. So what I've done is I've superimposed quite a high descent rate on that system. And you can see that what's happened is this tubular wake structure has disappeared completely and has been replaced by this toroidal, this annular structure, if you like, where the wake is recirculating around through the rotor system. And what you can see here is that all the vorticity is still there. It's just that the top topology, if you like, of the wake has changed. The wake is rotating in on itself and destroying itself through those instabilities in much the same way. And all that extra vorticity has been chewed up and thrown out in a different fashion through the top end of the rotor. So this is our fluid dynamic understanding. If you were pilots, then you would probably visualize vortex ring state in more of a fashion, something like this. So typically what we would do is we would plot forward speed in knots on the horizontal axis, and we'd plot the vertical speed perhaps in feet per minute on the vertical axis over there. And we would know that somewhere lurking down here at fairly high descent rates, and for certain forward speeds less than a certain value, we'd find something strange going on. You might experience the vortex ring state as thrust and power fluctuations in the most benign situation, but in the most aggressive situations, you might even experience something like reversal of the control derivatives. In other words, the thrust versus the collective pitch might change sign, that derivative. And in practical terms, what you might find yourself is accelerating in descent until something goes on. Either, unfortunately, if you're too close to the ground, you might impact the ground, or you'd fall out the bottom of the vortex ring state at a very high descent rate, which you'd then have to arrest in some fashion. So this diagram over here is from this fantastic paper, which I do suggest you read, which is effectively the story of the flight test program, which identified where in the flight envelope of the V-22 vortex ring state actually occurred. And this diagram here is actually a diagram of lateral automatic flight control system activity. In other words, this imbalance between the left and right rotors that was manifest by vortex ring state starting to occur on one of the rotors and not the other, this asymmetric vortex ring state, which is now thought to have precipitated this flip over and crash of the aircraft at Marana. Okay, so hopefully all clear at that particular stage. So I've tried to describe the physics of the vortex ring state. Now, if you're sitting in an aircraft that you're test flying, let's say an eVTOL or a helicopter or a tilt rotor aircraft, you really want to be sure that your engineers have discussed and established the vortex ring characteristics of those aircraft in proper detail. Now, the case that I tend to try to make is that the computational methodology that you use to establish what's going on in terms of vortex ring state is fundamental in actually giving you the correct results. There are various approaches that you can use. Some of the classical ones are the free wake approach or conventional CFD. And the danger is, and quite often when you look in the literature, is these approaches are not actually giving you the correct results. They don't actually locate the vortex ring state on that flight envelope in the correct part, or establish the magnitude of the thrust fluctuations or the danger post-flight in proper detail. So over the years, what we've done is we've developed a very, very specialized approach which analyzes these wake instabilities in gory detail and actually does manage to pin down the position within the flight envelope of the vortex ring state accurately. And that's crucial to understanding what's actually going on. Okay, so I could talk on this slide for an hour, so I'll skip over it briefly just to make that point. The other thing that you tend to find is that in the literature, there are a lot of sort of showboating studies, if you like, and you know, we can do that as well. Here's an entire aircraft in asymmetric vortex ring. This aircraft's got 8 rotors. These rotors over here are producing pretty coherent wakes. These rotors on this side of the aircraft are all producing vortex ring-like wakes, and this aircraft here is in asymmetric vortex ring. Now, you don't tend to learn terribly much from these sorts of calculations, unfortunately. So the best thing is to take a step back and do some decent science. And that's what we've tried to do over the last 10 to 15 years. And what we do is we go through the standard scientific approach. We establish a physical hypothesis for what actually is going on in the vortex ring state. And what we've actually found is that vortex ring occurs for a different reason to what the sort of standard textbooks or the basic write-ups of vortex ring would actually lead you to believe. Now, I harp on about wake instability, but wake instability, if you understand wake instabilities, you've basically got the understanding that you need. Wake instability is the primary physical mechanism that is responsible for the onset of the vortex ring state. So what I've shown in this diagram over here is a cut through a developing rotor wake. And again, here you can see the individual tip vortices, but those tip vortices then tend to coagulate, and the wake goes unstable and eventually turns into this giant mess down at the back end over here. And it's the development of those instabilities which results in the rotor wake changing from this tubular structure into its annular or toroid or vortex ring state. Why is that different to your classical explanation? Well, you've probably seen in the literature the vortex ring described as this idea of descending into your own wake. That's very misleading because it's not really that you're descending into your own wake. You end up mispredicting the vertical descent rate at which vortex ring state occurs if you take that particular perspective. What's actually going on is that there's a critical descent rate at which these wake instabilities gather up and start biting the rotor. If you speak to Claude Bouchard, he talks about this wolf in the wake, and his idea is of this wolf coming up and grabbing hold of the rotor. And what that really is these wake instabilities changing their structure and ending up, in fact, modifying the entire geometry of the wake itself. So the basic model that we adopt is that there are 2 factors going on within these wake instabilities. First of all, these wake instabilities can propagate down into the wake at a certain speed. But secondly, these wake instabilities can grow. And the whole mechanics of vortex ring is a balance between this growing and convection of these wake instabilities and those instabilities as a result either being swept down into the flow behind the rotor or in fact catching up with the rotor and changing the fundamental structure of the rotor wake. Now, there's a lot of mathematics and a lot of physics behind that. I'm not going to get and talk about that in too much detail, but if you sit in more detail, then there's an hour-long lecture on my website where I deal in detail with the physics and how we now understand the vortex ring state in terms of this growth and propagation of wake instabilities. But let me try to show you in some detail what's actually going on. So this representation over here is a sort of multimedia presentation of what's going on in vortex ring state, if you like. Here's a picture of the wake as it develops. Here's a picture which is a sort of a cartoon diagram of how these instabilities develop within the wake. So they start at the rotor, and as they sweep down into the wake, the instabilities grow in strength and size. And so what happens to these instabilities as we increase the descent rate of the system? And what you'll see is that the wake is going to change through a variety of of sort of gradual morphological modifications until a critical descent rate is reached, in which case the wake changes from this tubular structure into the toroidal vortex ring state. And if you're a bit more performance oriented, then this diagram over here will be of interest. This is the vertical speed on the horizontal axis here, non-dimensionalized by a factor which I'll talk about more in a little bit more detail, and the power on the horizontal, on the vertical axis over here. And you can see that there's sort of intermediate regime here where things start to go a little bit wobbly, and then the vortex ring regime here, which is characterized by these fairly large and recurrent thrust fluctuations. So that's with the system in horizontal flight, as I tried to indicate with that arrow over there. And as I increase the descent rate, watch what happens. Here's the point at which these instabilities lead to the trashing, if you like, of the wake behind the system. And watch what happens as I increase the descent rate. You see, as I increase the descent rate, the part of the wake which is dislocated by these instabilities eventually catches up with the rotor itself. Then as we reach a critical descent rate, the wake changes its character into this toroidal form, which is the vortex ring state. Now, if I didn't include that analysis in terms of the wake instabilities, my system would still be in perfectly clean air over here. In fact, if you don't include the instabilities, then you over predict the onset of vortex ring in terms of descent rate by a factor of about 2. Okay. So that's just finishes up. That's deep within vortex ring state. And you can see the rotor wake clearly in this toroidal form, with all the remnants of the wake being spat out the top there in an incoherent stream of vorticity fragments. Okay, so what do we do about that? Well, the interesting thing about that theory, if you analyze the wake instability in terms of the growth and the convection of these individual instabilities, is that you can come up with a very simple analytic model for where the vortex ring boundary lies on the flight envelope. And don't get too hung up on the mathematics of it. Essentially, the early model was fairly heuristic in character. This is it written in mathematical form: mu bar x and mu bar z. Mu bar x is the horizontal forward speed, non-dimensionalized in this case by the hover-induced velocity. The mu bar z is the vertical velocity, similarly non-dimensionalized. Why I include this form of the model here is that we were able to go back a few years later after this original model and revise the model to show that it actually was a specific case of something far more general, which was very interesting to us. The important thing about the mathematical structure here is you might recognize it from your high school mathematics. It's an x squared plus y squared is equal to z squared type of equation, which is the equation of an ellipse or a circle, if you like. And the term on the right-hand side over here is the radius of that ellipse. So what we're effectively doing is we're defining an elliptically shaped region on the flight envelope in which the system is subject to the vortex ring state. So forward speed over here, vertical speed over there. Outside this particular elliptically shaped region, we find that the aircraft is not subject to vortex ring state, but vortex ring state occurs, or the aircraft becomes susceptible to vortex ring as we cross that boundary. Now, the really interesting thing about this equation is that the right-hand side, or the radius of the ellipse, scales with the thrust coefficient of the rotor. And we know that the thrust coefficient is proportional to the disk loading of that rotor system. So this is where things start to get interesting if we extrapolate now to the eVTOL case. And I'll show you why in a second. Okay, so I'm going to use this formulation over and over again. I'll expose it to you a few times so that you'll get used to it. But what I'm going to do is I'm always going to present, being an aerodynamicist, I'm going to present things in non-dimensional fashion. So forward speed, I'll always non-dimensionalize by the hover-induced velocity, vertical speed likewise. And what that will mean is that the vortex ring regime remains static in shape on that particular boundary. Now, okay, we've got our nice analytic model. How does that compare to the data that we have available? Well, the answer is fairly well. This is the collection of just about all the experimental data that happens to be out there, from some very, very early flight test data through the famous Japanese experimental sets of data, which were so influential in the V-22 exploration, through to some rather modern data, again on tilt rotor aircraft, as established by Betsina in the aftermath of the V-22 incident. And you can see that this vortex ring boundary encapsulates the experimental data fairly well. Now, the thing to realize is just how broad brush Perry's model actually is. This is not a vortex ring onset boundary for any specific aircraft. It's a very general, generic idea of where vortex ring state might occur. So if we were analyzing a particular aircraft, we might expect some differences between the actual location of this boundary and what Perry's model actually predicts. So Perry's model doesn't take into account things like twist distribution, blade tip shape, all these slightly more subtle characteristics of the rotor that might lead to changes in the vortex ring state behavior. So bear that in mind throughout the presentation here. I'm going to present almost all my results in terms of this generic Perry model, but if we were talking an actual aircraft, then we perhaps need to actually generate the particular boundary for that particular vehicle. Now, the basic premise of this presentation is going to be that we know that vortex ring state is a real threat to the helicopter community. If we look at the accident statistics, so for example, if we go to the NTSB Carroll accident database, we see that there's 79 results for settling with power. Okay, whatever that means, we know that there's a little bit of confusion as to perhaps what settling with power actually means. But there are 17 results in the NTSB Carroll database which apply to vortex ring state directly. Now, we know that proper attention to the phenomenon is presently obscured by confusion over terminology, lack of understanding of the physics and all this sort of thing. The basic postulate is, or the basic question I want to ask is the eVTOL community going to make the same mistake? Or are we going to analyze vortex ring state and understand its implications for eVTOL aircraft before these aircraft actually get too far down the testing route? And how can regulators help? This was the fundamental question that I took to the EASA meeting in Cologne. Okay, so I'm going to talk about three different aspects. I'm going to talk about trajectory and how the trajectory followed by the aircraft might influence its susceptibility to the vortex ring state. I'm then going to talk about maneuvers. So I'm going to complicate things a little bit by not only talking about the trajectory, but how the aircraft actually flies that trajectory. Does it roll? Does it pitch? Does it vector its rotors as it flies the particular trajectory? And then I'll talk a little bit about the urban environment, particularly in terms of gusts and in terms of vertiport design, and hopefully shed some light on perhaps where we should be going at the interface between design, between the testing, and between regulation. What I probably won't have time to cover in much detail is aerodynamic interactions. We know that the configuration of the aircraft has particular relevance to what sort of vortex ring state it actually gets itself into. But that's a large area to cover in a presentation, which is trying to be as broad as this particular one. But if you do go along to my website and have a look at the paper, you'll see that the original European Rotorcraft Forum version of the paper concentrates to quite a large extent on various configurational issues and shows things. So, for example, that if you have two rotors flying in tandem, you can end up in trouble that you might not expect because the wake from the rotor in front, as I've tried to show in this diagram over here, tends to interfere with the rotor behind and introduce or induce a sort of quasi-vortex ring state at a much earlier descent rate than you might imagine for full vortex ring onset full vortex ring state onset for that particular configuration. So
I'm glad you pointed that out as something else to dig into, because obviously that's a big concern to this group is this kind of interaction. And so you're saying that your website has a little bit more information on that concern?
It does. The original ERF paper talks in detail about that. But if it's a subject of interest, I'm quite happy to take questions either now or a little bit later in terms of
okay.
Just how configuration influences things.
Yeah, well, we'll belay the questions for a little bit. Let you roll. This is great.
Okay. Right. Okay. So in terms of the core presentation here, I'll skip this a little bit, but happy to come back to it if it's of interest. And of course, it's a subject of huge interest to me. This is sort of aerodynamics meat, if you like, how the configuration of the aircraft actually influences the onset of the vortex ring state. Okay, so let's go back to this model, the original, and I will use it in the form of the original Perry model. John Perry, who passed away a few years ago, was instrumental in defining this particular analytic expression for the onset of the vortex ring state. And as I described earlier, what it's really doing is defining this lobe shape, this elliptically shaped boundary on the flight envelope as defined in terms of forward speed and vertical speed at which VRS onset takes place. And the scaling parameter that we're going to use over and over again, I call it the induced velocity in hover. But what it really is the induced velocity in hover as modeled using simple momentum theory, the kind of thing that you'd find in sort of helicopter 101 aerodynamics. And if you go through the mathematics, what I'm really doing by non-dimensionalizing these axes in terms of VH is, in fact, I'm non-dimensionalizing in terms of the disk loading. So the higher the disk loading, the higher VH. And that's a crucial thing to remember. Okay, so as I increase the disk loading, I increase this induced velocity parameter that I'm going to use to scale all these diagrams by. If you're a mountain flyer, that's an interesting term to take note of. That's the density, of course. So in other words, this term actually gets bigger the higher the disk loading and the lower the density, or the higher the altitude at which you're flying at. And so my Swiss friends that I presented this work to at the ERF were very interested in this particular term over there and asked quite a few questions regarding its influence. Okay, so to ram this idea home a little bit, let's have a look at two helicopters that have very, very different disk loadings. This is a CH-53E, as you'll all recognize, and this is the militarized version of the Bell 206B. And if you have a look in their flight manuals, then the VRS onset boundary is described in terms of an onset of either light turbulence or severe turbulence over a range of descent rates for forward speeds less than the critical value. And so there you'll see the lobe for the CH-53. This is the lobe for the 206B. Now, those lobes look identical, and that's for a very good reason. This is what Shizu and Azuma's data way back when transcribed into the flight manuals for these particular aircraft. Now, these diagrams are not as similar as they look. You can see that the values on the horizontal and the vertical axes are very, very different. And so by the magic of PowerPoint, what I'll try to do is to rescale these diagrams so that the axes actually have the same units on them. And if I run that, yeah, there we go. Hopefully this will work. There you go. You can see that the aircraft with the much lower disk loading has this relatively tiny VRS onset lobe compared to the heavier loaded, the higher disk loading aircraft, the CH-53E. So that gives you a relative sort of a fairly broad brush appreciation of just how much disk loading can affect the part of the flight envelope that's subject to the vortex ring state. Now here's something else which is quite curious. If I have a look at all helicopters which have currently been designed, and I'm talking about the sort of classic main rotor, tail rotor designs, then what you find is that if you plot disk loading versus the log of the weight of those aircraft, then the values follow a very, very obvious trend. In fact, it's a very, very simple geometrical argument that you can follow to show that the disk loading is roughly proportional to the weight of the helicopter to the power of 1/3. And if you plot most of your conventional helicopters, then they gather fairly nicely around that particular trend line, with the exception of the V22, which lies way off that particular trend, much higher disk loading for the kind of weight that you would expect at that particular point in the diagram. So perhaps when the V22 first came into service, there might have been a little bit of a niggle there to say, okay, look, we're dealing with an aircraft which is not going to behave as per the traditional idea of how helicopters behave. And perhaps if VRS had been an issue at that particular state, maybe talking very hypothetically, we would have had a bit of forewarning of problems to come. Now, this is the interesting thing. If I take all the data that I have for E-VTOL aircraft and plot it on the same boundary, or the same diagram, you can see that E-VTOL aircraft are a completely different kettle of fish. They obey a completely different trend. So you've got some vehicles down here. Now, okay, I should backtrack a little bit. I should have something like, how many points should I have on this diagram? Something like 600, right? But the amount of reliable, accredited data that's available out in the domain at the moment is a little bit limited. And that's a bit of a concern of mine, that the folk are actually hiding the weight disk loading information for good commercial reasons, I guess. But certainly it'd be very nice if people were a bit more transparent about that particular information. Anyway, 3 different types of eVTOL aircraft. You've got the helicopter-like eVTOLs down here, which obey a particular trend which is very similar to that of conventional helicopters. You've got the very high disk loading devices up here, the sort of jet type devices. This is not the one that you might think it is, but these are aircraft which are more jet-like than propeller-like in their design. And then over here, these are the typical lift and cruise stroke vector thrust machines in this particular range over there. The point being here that they have very much higher disk loading for their weight than might be expected by a classical helicopter engineer. Okay, so what? Well, let's rehash this idea of disk loading and what its influence is on the size and shape of the vortex ring domain. So what I've done here is for a bunch of helicopters that you'll recognize: the Robinson, the Bell 207, and Bell 206, sorry, CH-53E, the MV-22. These are the vortex ring onset boundaries plotted in rail units. In other words, feet per minute versus forward speed. And so you can see for the V-22, no vortex ring state takes place until you're traveling at forward speed less than about 42, 44 knots. And if you're flying at descent rates that are less than about 2,000 feet per minute, then you're going to be clear of vortex ring. But there's this portion of the flight envelope here where vortex ring onset can take place. If you're in the much more lightly loaded Robinson R22, then you can see that the onset speed for vortex ring state comes way back down to about 18 knots, and you'll encounter vortex ring state if you're sitting at descent rates below probably about 800 to 1,000 feet per minute descent rate. Now let's plot those eVTOL aircraft on that same boundary. So they're my aircraft 1, 2, 3, and I'll use those over and over within this presentation. You can see this aircraft over here, this aircraft 1, has a vortex ring onset load, which is quite a bit bigger than, well, it sits out here, if you like, in terms of somewhere between the CH-53 and the V-22, which is an interesting observation to make. Now, it's not necessarily a bad thing to have a high disk loading, because what that does, of course, is it increases the distance between horizontal flight and the descent rate for onset of vortex ring state. So it's not the location of the VRS boundary per se, but as I'll try to show you in the next slides, it's how that vortex ring state boundary intersects with other considerations in terms of the design. Configuration, we're not going to talk about in too much detail right here, but what I will talk about in quite a lot of detail is trajectory and maneuver. Okay, so let's talk about trajectory. Let's see how the trajectory followed by the aircraft might influence its susceptibility to vortex ring state. Now, what I'm going to do is I'm going to kind of make up a trajectory that the aircraft is going to fly, a fairly realistic trajectory where the aircraft is going to come down into, this is a descent and landing trajectory. So the aircraft starts off somewhere up here and ends up at 0 forward velocity and 0 vertical speed on the ground, most hopefully. Now, of course, if the aircraft trajectory intersects the vortex ring state onset boundary, then it's not going to follow the intended trajectory. It'll follow some sort of escape trajectory, which hopefully will bring the aircraft to the vortex ring state in some sort of condition that is still flyable. But I won't worry too much about the dynamics once the aircraft is intersected with the vortex ring onset or the boundary there. Now, the other thing to remember is, because I'm using this non-dimensional representation, the vortex ring onset boundary remains the same, but the trajectory scales as I change the disk loading. So if this is my nominal trajectory in blue, what's going to happen is if I decrease my disk loading, then the trajectory is going to expand out by expanding about the origin equally in terms of vertical speed and forward speed, non-dimensionalized in this fashion. And if I go to higher disk loading, what's going to happen is my trajectory is going to crunch in towards the origin. So that's the basic effect. If I have a nominal trajectory and I fly the same trajectory using different aircraft with different disk loadings, then what's going to happen is the trajectory is going to scale in and out with respect to this VRS onset boundary. So to show you what I mean, let's have a quick example. Okay, so this is a trajectory which I'll call a fairly shallow descent. The aircraft follows a fairly benign descent down to its landing point over here. Same trajectory flown by two different helicopters, the 206B and the Robinson R22, and here flown by my eVTOLs 1, 2, and 3 with their various disk loadings, 1 being the highest disk loading, 3 being the lowest disk loading. And what you can see here is that in all the helicopter cases, the trajectory is benign. It has a fairly significant skirt around the onset of vortex ring state. But because of the higher disk loading of these eVTOL aircraft, they are brought much closer to the onset boundary. Now, the point to take away here, I think, is that if we try to structure our trajectories based too much on given helicopter experience and try and extrapolate that helicopter experience directly onto eVTOL aircraft, we could be running into problems because of this extra little niggle in the argument, which has to do with the disk loading of the eVTOL aircraft themselves. what the eVTOL disk loadings tend to do is shift a helicopter trajectory much closer to the onset of the vortex ring state than perhaps might be appreciated. Let's over-egg the situation. Let's let's change where we do our maximum descent. Let's bring our maximum descent much closer to our descent rate much closer to the landing site. You can see what's going on here is that the helicopters are skirting very uncomfortably close to the onset of VRS at the knee of the vortex ring boundary over here. But in this case, these eVTOL aircraft are pushed over the vortex ring onset boundary and will experience problems with vortex ring state. Okay, so that diagram is just to show you what happens if you start to make your descent a little bit more aggressive. Now, this diagram is presented because I think that well, largely because of what I'll show you a little bit later. And that's essentially that some of the eVTOL operational models make provision for these very, very steep final descents, especially when it comes to some of the EASA regulations for vertiport design. And in that case, you can see helicopters would struggle with vortex ring onset, most definitely, but the eVTOL aircraft are pushed into a regime where things are untenable. And this, to a certain extent, is a concern that if the operators are not and the manufacturers are not pushing for a proper cognizance of vortex ring state, but the regulators are regulating in such a fashion that they're promoting these highly constrained trajectories, we might be looking for trouble when it comes to the interface between regulation and what is practically achievable in eVTOL design. So this diagram should be borne in mind in terms of what I'm about to present a little bit later.
Question for you on that.
Yeah.
That is alarming as you presented it, but isn't the bottom line really just to understand your aircraft and ensure that you don't operate, slow down your descents? And that's really the name of the game, is to understand where those limits are?
That's absolutely correct. So the take-home message here, if you like, refers back to how I introduced this particular work here, and that is the VRS onset boundary should not be seen in isolation. It should always be viewed in terms of the trajectory that you're trying to fly. So the best way of ameliorating the onset of VRS is to design a trajectory which actually takes the boundary's location into account. And if you're not doing that, then that's certainly going to be a trouble spot. But what I'll show you later is that the industry does tend to be moving in some quarters towards a sort of over-regulated situation in which manufacturers are actually going to find it very difficult to find a trajectory which does meet the requirements, put it that way, and simultaneously avoids vortex ring state.
Excellent, thank you.
Okay, so that's trajectory, and it's a little bit of a warm up, if you like, for what comes next. Okay, so take home messages. Okay, we know eVTOL disk loadings are higher than those for conventional helicopters, and what those trajectory diagrams really shows that the disk loadings are not high enough to exploit this favorable shift in the vortex ring boundary that I described earlier. In other words, the idea that actually by increasing your disk loading considerably, you push down the top end of that boundary to much higher descent rates than you would have with let's say, classical helicopter type disk loadings. Trajectories that tend to be safe for helicopters tend to be less so for eVTOL aircraft. The implication being that if your design and your operational procedures are heavily influenced by helicopter experience, then perhaps you need to be a little bit careful. And certainly this idea that eVTOL operation in urban areas, given heliport and vertiport design, and particular noise abatement and those sorts of issues, I'll show you in a lot more concrete detail why these might need to be revisited in the light of the danger posed by the VRS state, at least in terms of some of the regulations we have over this side of the Atlantic Ocean. Okay, so let's complicate things up a little bit. Let's add some maneuvers and see what that does. Now, the thing to bear in mind here is that the aerodynamics of VRS is the aerodynamics of the rotors, all right? So up to now, I've been kind of hiding the fact that the rotors might be operating in somewhat different conditions to the aircraft overall. If you're measuring airspeeds at, let's say, the pitot probe on the aircraft, that might not be particularly representative of the flow conditions that the rotors themselves are experiencing. And there are two particular cases where I can illustrate that quite clearly. The first is if you have side-by-side rotors, so something like your classical tilt rotor configuration, and we look at lateral maneuvers. And the second interesting case, which I'll show you, is that if we have vectored rotor thrust, so in other words, we use thrust vectoring to accelerate or decelerate the aircraft during conversion and descent to landing. So this is the typical case that we find if you're looking at side-by-side rotors. And what the scenario that I've established here is, okay, the aircraft's in descent, and at some critical descent rate, what we do is we decide to turn onto a different heading. So we instigate some form of bank angle, the aircraft rolls, establishes itself at a pitch rate and a roll rate and a yaw rate to keep that, roll rate and a pitch rate to keep that turn going, and then comes back out of the turn again onto a new heading. Now that's the trajectory that's followed by the aircraft as a whole with respect to the VRS regime. But the rotors, because they're experiencing a different aerodynamic environment to the aircraft as a whole, see a whole different trajectory on this particular diagram over here. So there's the port rotor as it rolls down, and then as the aircraft establishes itself in a steady turn, and then it rolls back out again. You can see how, because of that rolling maneuver, that particular rotor could have an encounter with the vortex ring regime. On the starboard side of the aircraft, on the other hand, because this rotor happens to be going up, it actually moves away from the vortex ring regime because of this upwards flow that's induced through the system in local coordinates, if you like. And so what you can end up is with this very, very dangerous situation where one rotor, or the rotor on the left-hand side in this particular case, goes into the vortex ring state. The rotor on the right-hand side stays in normal operating conditions, and the pilot or the control system of the aircraft has to do something to rectify that situation. In the case of the Murano V22, in that case, the pilot and the control system were not configured to understand what had happened, let alone to make any corrective actions. And so that was a particularly pernicious example of asymmetric vortex ring as a result of a turning maneuver. This is a slightly more subtle example here, where we're using thrust vectoring to decelerate the aircraft. So we tilt the rotors back to some extent to bring the aircraft down from its cruising speed to zero and stopping the aircraft on the ground. So in this diagram over here, what I've tried to represent is the change in the thrust vector with distance along the trajectory. And the interesting thing is, if you change the aircraft drag, then the amount of thrust vectoring that you require to decelerate the aircraft, as you might expect, changes. And as a result, well, here's the trajectory of the aircraft, the nominal trajectory, and here's the trajectory of the rotor with respect to the VRS onset boundary. And you can see that as we decrease the drag of the aircraft, we rely more on this rearwards tilt of the rotors to decelerate the aircraft. And the rearwards tilt of the rotors, of course, ends up establishing a vertical component of the flow through the rotor, which can then bring that particular rotor closer to the onset of vortex ring state. In this particular case here, what I've indicated is that for an aircraft with the lowest possible drag, where the most rearwards vectoring is required, you can actually end up with a situation where vortex ring state poses a problem. Now, of course, we know a lot of the current eVTOL designs are priding themselves on the slinkiest, lowest drag design that can possibly be designed, and in a way, okay, that needs to be handled with care. Palliative techniques, difficult, because drag tends to changes with the square of velocity. So once you're down at the bottom end over here, you're kind of caught again between a rock and a hard place. Where do you actually get the decelerator force that you require for the system? But okay, this is another example where the subtleties of the aerodynamics of the vehicle can actually come to bite you as far as the vortex ring state is concerned. Okay, so the basic take home here is that some elements of eVTOL configurational design might increase the chances of entering VRS during descent and landing as a result of maneuvering. Okay, so in terms of the design of these aircraft, it's really a strong case, I think, that folk need to go and have a look and just make sure that there are no little hidden aspects of the dynamics of the aircraft that have been built in that might induce problems with respect to the onset of vortex ring state. Now let's have a look at the urban environment in some detail. And we'll look at two different aspects. First of all, gusts in some detail, and vertiport design in the last part of the talk. So the nice thing about this analytic model is that you can really get your hands dirty with it. It's a bunch of equations which you can manipulate, you can substitute into, and you can end up with drawing inferences from the basic model that can be used in practice. And one of the really interesting inferences is in terms of the susceptibility of eVTOL aircraft to enter the VRS as a result of gusts within the urban environment. So in fact, what you can do is you can define a horizontal gust margin and a vertical gust margin in terms of the position of the trajectory with respect to the VRS regime at any particular forward speed and vertical speed. And you can translocate that onto diagrams like this in terms of limitations on how the aircraft can actually perform in order to avoid VRS as a result of entering gusts. Now, these diagrams at first glance are a little bit difficult to interpret, but really what you have to do is you need to define yourself a trajectory which allows you, if you like, to creep under the boundary that's given for that particular aircraft over here. So in terms of vertical gust margin, you have to keep your vertical speed below, at this particular descent, at this particular distance along the trajectory, below the curve for that particular aircraft. Similarly over here, there's a juggling act required. You have to keep your aircraft at a vertical speed which is greater than, which is again below the particular descent rate that's given in this particular diagram over here. And what you'll see here is the classical helicopter case transposed. It's what you might expect. It's that if you're at fairly high forward speed, what you find is that your main the main bugbear to avoiding VRS is velocity, is gusts from behind, which tend to decrease your relative velocity, your airspeed. Whereas if you're operating at fairly low forward speed, then the situation changes, and the bugbear is then the upwards gusts that might increase your effective descent rate. In fact, so that's the idea here. Now, if your trajectory skirts too close to the vortex ring onset boundary, then you can see that those margins are effectively reduced. So what I'm proposing here is effectively that there's an analytic approach to defining these trajectories in terms of gust margins, so getting some idea of how safe you can actually be in descents with respect to gusts within the urban environment once you've quantified the actual gusts that you're expecting to encounter within a particular urban scenario. So there's hope here that we can use these analytical models to try to improve the safety of eVTOLs to the onset of VRS once we incorporate models like this, for example, into optimization procedures for defining the trajectories. Now, let me finish off by talking a little bit about vertiports. Now, you'll find on the web a very interesting document, which is this EASA PTS VPT DSN, which is a set of putative requirements or design specifications for an urban vertiport. And this is very much in the European context. You can see this is a nice Parisian city. Here's a vertiport with some sort of eVTOL aircraft over here, very much integrated into the community. A man over here walking his baby in complete blissful ignorance, if you like, of this vehicle sitting just across the way over there. Now, this is the idea that's being proposed. This is very much not the American idea. If you look at it, the sort of standard American idea for a vertiport is to have this approach surface, if you like, which has a fairly benign approach angle, and then this would be the FATO on which the aircraft would be designed to operate. What the EASA proposal does is it adds this immense funnel down below, through which the aircraft is supposed to descend to land on this space over here. Now, okay, let's discuss that in a little bit more detail, see if it actually is how that will interact with eVTOL design. So here's a sort of slightly schematic version of that vertiport design. So here's the approach surface, if you like, and there's this funnel that leads down to the deck. So gamma, as I've marked here, is the shallowest descent angle that you could follow, if not to collide with the basic surface over there. Beta is the shallowest descent angle that you could actually enter the funnel at if you were to miss the central landing site and try and accommodate yourself within the available designated landing area. And this is the actual trajectory that you might want to follow to get into that particular landing site. Okay, so let's transpose that onto our old axes, the forward speed non-dimensionalized by the hover-induced velocity and the rate of descent over there, 0, 0 over here. So there's my minimum glide slope. There's my minimum glide slope to actually enter that last particular area. And this is the glide slope that I choose to adopt to end up actually landing properly at the landing spot in that particular scenario. Okay, so this point D is crucial. Where does that point D lie on this particular boundary? And the reason it's important, obviously, is that we have this vortex ring regime sitting just below there. And so what we want to do is we want to put D outside of the vortex ring state. How do we do that? Well, there are two approaches that are available to us. First of all is that we constrain D to have a very low descent rate, or we design our vehicle to have a very high disk loading. So in other words, when we non-dimensionalize, we sit outside of the vortex ring state regime. Okay, seems all well and good. We have a pretty good idea of how we might change the design of our vehicle or the operating conditions so that we can meet the EASA constraints on their design of their vertiport. Now, let's focus in a little bit on what's actually going on there. That's our VRS margin, of course. Okay, and this is recapitulating. That's shifting to a lower descent rate at that particular decision point or to a higher disk loading. Okay, now let's throw a little bit of more wood on the fire, so to speak. We know that outwash is a problem because outwash also scales with respect to the disk loading. We know that the strength of the wall jet is proportional to the disk loading, which is proportional to the hover-induced velocity through the system. So we also know that complex configurations for vehicles can play havoc with the outwash pattern. We know, for example, in a tilt rotor, we have this particular zone that runs along the length of the aircraft in which the outwash effects are highly magnified. And we recently had a situation in the United Kingdom where one of our US Marine friends came to land at one of our hospital landing sites, took off a few hours later and took much of the landing site with them. Extrapolate that situation to your nice little Parisian cafe, and you'd end up with something that looked like a Caribbean typhoon had passed through in that particular situation. So we want to try and avoid that particular situation. Now, the thing is, we know quite a lot about outwash. We've done a lot of studies in terms of helicopter brownout. We know that the outwash pattern is complex and configuration dependent, as I said, but we also know that some very simple scaling laws apply. First of all, that the outwash velocities scale with the induced velocity through the system, or in other words, with the disk loading. And secondly, that the cumulative damage caused by the outwash scales with the time taken to descend and the outwash multiplied by the outwash velocity. So interesting here, the disk loading then gives a limit to the maximum, the outwash velocity itself gives a limit to the maximum tolerable disk loading in the setting. Whereas if we look at this multiple of the time taken to descend and the outwash velocities, then that gives us a limit to, well, the amount of cumulative damage that we can tolerate, and that's expressed in terms of the lower limit to the tolerable rate of descent into the vertiport. Okay, so what I can do is I can add a second boundary onto this diagram over here, which is this outwash parameter written in terms of VH, the outflow velocity, if you like, multiplied by the time in descent. And you can see that if I put these two boundaries on this particular diagram, we're caught between a rock and a hard place. If we have an aircraft with too high a disk loading or too low a descent rate, then we end up causing damage to the vertiport as a result of outwash. If we have too low a disk loading or too high a rate of descent, then we enter the vortex ring state regime. So we have to thread the needle, if you like, in terms of the aircraft design and in terms of the trajectory design, so that we can end up accommodating these regulatory aspects of the vertiports. And seriously, I think the only solution there is kind of a bit of give and take on both sides. You can see very easily how if we constrain the vertiport to being too small, the angle that we allow ourselves over here becomes almost vertical, and we end up with an intolerable situation where we might actually design ourselves out of existence. And that's perhaps the greatest worry here, that the regulation constrains aircraft into extinction. Okay, so in conclusion, what I've shown is that the disk loadings for eVTOL aircraft can improve gust ride quality but reduce gust margins with respect to the VRS, because the margin is reduced because of the enlarged size of the VRS onset boundary. We'll perhaps need to design our trajectories with local atmospheric conditions and appropriate margins against gust-induced entry into VRS in mind. And I've shown you some techniques which are in slightly sort of nascent stage that we're hoping to develop into something a little bit more extensive as time goes on. And I've shown how these, particularly this particular proposal for EASA vertiport design could actually end up paving the way, in looking at it in a very positive light, paving the way to perhaps folk getting around the table and saying, okay, look, there needs to be some compromise between design and regulation to find a happy medium where the regulation actually enhances the chances of the industry being successful. Okay, so last slide. Evidence to suggest that VRS for eVTOL aircraft will be as serious a problem it is for helicopters. I think I've shown that in gory detail. I think we can learn something from helicopter experience, but we need to be a little bit careful about trying to learn too much or extrapolate too much. We do need to do the additional groundwork to address the specific issues that are posed by the new technology that eVTOL poses for us. And I think we're sitting, and I've talked about this in legs, it's my sort of famous dinosaur speech, if you like, that eVTOL aircraft are kind of at this cusp where we've been in this honeymoon phase for a large amount of time, where the potential and the sort of business case has been made for these vehicles, but now we're starting to see more and more of these aircraft coming out of this visionary phase and into flight testing and certification. And I think what we're going to find very, very interestingly is as we enter that particular phase, we're going to have to focus very much more on the engineering aspects of the problem. We have to bring out the most detailed, most accurate aerodynamic analyses and trajectory analyses and dynamic analyses that we can. And if we do that, then I think we're onto a good thing, and I think the industry can advance. The problem is, of course, if we stay stuck in a sort of realm of denial, and we let the hype and the kind of unsubstantiated expectations take over, and don't actually address these hard technical issues, which we really should be, based on previous experience. Okay, so that's where I'll stop. I've hopefully left a few seconds for some questions. I'm going to try to get out of this if I possibly can, and head back to the live presentation.
This is awesome. You have done such a wonderful job in putting all the pieces together in a clear manner. So thank you very much. We have a few questions that have been written on the text, so I'll start walking through those. And while you guys online can think about unmuting, and then asking your questions yourselves. Here is one. Let's see. Is there an implication that VRS entry is also a function of power applied, and how does it change for multi-rotor systems? Nick Allen, did I get your question right?
I dropped a whole bunch into there, but yes, that's going to be definitely one. You talked about the interaction effects for the VTOL for the Osprey, where you have the two rotors. One could assume the same thing, CH-47, for example, but there's a lot of eVTOL aircraft out there that have way more than two. The Lilium jet, lift aircraft, you know, I forget what the Lilium has, 30 something. How does that end up? Has anybody tried to do any extensive modeling on that? Any idea like what you're starting to get when you get those really weird dynamic interactions between all those different rotors?
Yeah. It's a good question. It plays directly into the idea of aerodynamic interactions and what effect the configuration of the aircraft has on the onset of vortex ring state. Now, I'll not make a claim to be all-knowing in this field. There's a tremendous amount of work that we still need to do, especially in terms of defining parametric or developing our parametric understanding of what's going on. So how many rotors is the best? What is the configuration with respect to each other that's the best in some sort of generic terms? And those questions are still open. What we do know is that the interactions between rotors has a profound effect on the dynamics of the system, both leading up to and into the vortex ring state. So multi-rotor aircraft behave quite differently. We've done some calculations on as many as 8 rotors to show that there are various very interesting phenomena to do with the onset of vortex ring state. So the two that spring to mind immediately are, first of all, that if you have one rotor on the system going into vortex ring, it's generating this collapsing wake behind it. Now, where does that collapsing wake go? Well, if you happen to have another rotor sitting just behind that particular system, then that collapsing wake is going to end up interfering with the wake that's developing on the system behind. Now, that might not precipitate vortex ring state on that rotor that's sitting behind. Sometimes the aerodynamics of these rotors is actually quite robust to some quite extreme perturbations. But there is the possibility that we've seen that rear rotor can enter a regime of huge thrust fluctuations, which are not vortex ring-like, but they're much more like flying through some intense, ultra-intense form of turbulence. So that's one particular effect. The other is the idea that the rotor sitting elsewhere within the system can actually be quite susceptible to perturbation by a rotor that's going into vortex ring state on its own. So what you can end up is with a cascading situation where one rotor going into vortex ring state starts to promote vortex ring state in a sort of a ripple effect through the remainder of the system. And that's the situation that worries me a little bit, because it kind of goes against the whole principle, if you like, of using multi-rotor systems and some of the benefits of multi-rotor systems, particularly in terms of the E in eVTOL.
Yeah, that's not going to be easy. Hey, Danny, did you want to go hot and ask your question? I can start for him while he's there. You go.
Yeah, it took me a second to find the buttons. Yeah, I'm just curious how you put out some data that's sort of an empirical rules of thumb, if you will, and how is the non-traditional structure? You know, it's sort of an airplane with a fixed wing in proximity to the rotors, and compared to a helicopter rotor, they're small. How are those going to play together, and how will they impact potentially in a negative or safety issue with what's traditionally been done in rotary wing? And I put the caveat that I've got no experience in rotary wing, so if it's a naive question, then I'm happy to educate myself elsewhere first.
No, it's absolutely not a naive question. Again, it plays to the idea of aerodynamic interactions and just what effect those have within the system. So now you've got a destabilizing wake, and you've got a wing in sitting inside that wake potentially. So we know that the aerodynamic interaction between the wing and the rotors, if not properly controlled, can lead to relatively large, depending on the flight speed, but it can lead to relatively large perturbations in the loads that are generated on the wing as well. Now, whether that then manifests in terms of roll excitation on the aircraft, you can imagine, let's say it did, you might then start to precipitate some sort of roll oscillation, which might then influence rotors which are further out, and you might end up in a rather nasty situation as a result of those interactions. Or what you might find in certain configurations, if you get the wing in the right place, is that you might actually be able to use the wing to duck the wake away into some benign state, or into some benign part of the overall envelope of fluid which is surrounding the vehicle, where it doesn't actually do much damage. So these are the kind of detailed design questions which folks should be asking. They're very good questions. It's what if we change the rotor configuration with respect to each other? What if we hide a rotor within the shadow of a wing? What if we bring the rotor into the aerodynamic environment that's generated by the wing? These are all design considerations which can be used to at least two different things. They bear on the susceptibility of the aircraft to vortex ring state, but secondly, they might be able to be used as palliatives or effective methods of controlling or circumventing the vortex ring state. We just don't know enough about the situation just yet.
Excellent. Thank you. What I think, Peter, I think his answer also answered your question earlier, or did you have a more refined version on your question that you wanted?
It mostly did. The coupling of the wakes across multiple rotors is one concern, and the fact that there seemed to be a feedback effect in your paper. But the other half of my question was, can I think about that as simply increasing the perimeter of the VRS ellipse, or is it more complex shape than that?
Yeah, it's a good question, Peter. what I didn't really show in my talk is that there are two roughly equivalent ways of having a look at how vortex ring takes place. The one is effectively by presenting things in terms of the non-dimensionalized diagram where the lobe stays in the same place. The other is presenting in terms of real velocities where the lobe shifts and the aircraft, if you like, stays in the same place. In terms of interactional aerodynamics, what we can expect is that the lobe shape will change as a result of interactions and all the perturbations to the conventional fluid mechanics that renders the Perry model a little bit, well, not powerful enough to deal with the complexity of the aerodynamics. So I'm suspecting that for a rail aircraft, what you will see is that the lobe will be a lot more jagged and a lot more fully featured, if you like, than in the Perry model. And that's something that individual designers should really go and investigate. Is just what their lobe looks like for their particular configuration. With rotors with all its lifting surfaces and so on, all interacting.
That makes sense. Excellent. Thank you, Richard.
So what I would like to do now, and we're going overtime, of course, but this is just too good to let go. So I'm going to ask another couple of questions, again, associated with flight test and certification. So what we've been talking about so far has largely been you figure out the behavior of your particular aircraft, you somehow model it and you validate the model and you show the authorities that you're not going to violate, right? Your operations won't violate that. That's pretty fair. Now, and this ties in perfectly with a lot of the conversations we've been having in our council about, hey, doing just that and having alerts on the aircraft to let you know when you're getting near limits and so forth. So let me shift that theme to this new question. Beyond mapping it out in advance, is there potential to monitor it in flight, just like you have a stick pusher, looking at angle of attack? Is there something we can do to monitor this so that operationally, because there's so many variabilities in wind and gust and everything else, is there something we can do to monitor ourselves and then escape when necessary using the Bouchard technique or anything else? Is there any thought, any possibility of doing that?
It's yeah, Al, that if you like is the holy grail. I think it's to have active sensing of sufficient parameters on the aircraft so that you know when you're approaching the danger zone, so to speak. It's a tough ask, but I wouldn't give up on it, so to speak. You mentioned Bouchard. If you speak to Claude, he has such an intrinsic kind of imprinted idea of sort of impending doom on the rotorcraft that somehow you want to sort of offload his what did you call it? Almost his innate understanding of the system into some black box, which could then say, oh, I am, yeah, but the wolf is catching up with me.
We just need the mind meld.
Yeah, exactly. Now, a lot of progress has been made in tilt rotor aircraft in doing that. For example, the tilt rotor VRS is a lot better understood than it was way back when the Marana accident took place. And to a large extent, yeah, there's quite a lot of machinery on board to enable pilots to give pilots at least a warning, at least when they're approaching the NATOPS boundary, if not anything more significant than that. The problem is actually translating from, what did you call that? That's a fairly sort of regulated onset of vortex ring state under conditions which are pretty well encapsulated. What you're talking about is more of all singing or dancing VRS onset indicator that would cope with, let's say, if you were flying alongside the Empire State Building or over somewhere else, whatever it was. Maybe artificial intelligence might eventually yield a solution to that. But yeah, it's a very open question, and I'd be speculating completely as to what the solution would be.
Okay, good. Well, at least I'm more aligned with you now. Thank you. Okay, folks, did anybody else have any questions?
Quick one I had up here was, am I reading your equation correctly, saying that the vortex ring state region changes dynamically with disk loading during flight?
Yes, yeah, exactly. So the model that I presented is what we would, if we were slightly more rigorous, we'd call that the quasi-steady Perry model. So what we assume is that if your thrust increases and your disk loading increases as a result, the lobe expands proportionately with that increase in disk loading and would contract again as the loading. Yeah, so it's a very dynamic animal.
So now this is a lung, where that lobe is actually a lung. That's
right, and it's in 3 dimensions. It's like a potato. It's an apple-shaped thing which expands and contracts. It's quite weird. But one thing to bear in mind as well is importantly that's a quasi-static analysis. Now, experience from the V22, some of the early tests showed that if you're in a dynamic situation, if you're maneuvering, if there's a fair acceleration on the aircraft, then the vortex ring onset is somewhat different to if you were flying in a sort of quasi-steady fashion and slowly increasing your descent rate. So the dynamic effects, the accelerative effects as well, which you need to incorporate.
It sounds like the most dangerous combination would be pulling out power while turning and descending.
Yeah, something like that. You might find pulling power slightly delays the onset, but then certainly the turning might, when that onset takes place, you might end up with a very, very sudden vortex ring onset. But then again, that's speculating again. I'd love to do the analysis and the calculations at some
That's
stage.
interesting because all those charts in the manuals for the 206 or whatever treat it as a static place. And it seems like if you're turning in your descent, or if you're dropping power in your descent or anything along those lines, you could easily get into a place where the hard line, 30 knots or 40 knots or whatever you decided is for your aircraft isn't going to apply.
Yeah, absolutely. Yeah.
Hey,
oh, go ahead, Andre.
Yeah, thanks for the presentation, Richard. If we think as flight testers in a way to flight test this in the future, then of course we're going to try to do it up and away and then try to predict what's going to be down below. And you showed that density is one of the parameters. That correlates well. Is that the only parameter we should be looking for?
Density and weight, effectively. And so those are the 2 parameters that govern the size of your vortex ring lobe, at least in its broad extent. And then yeah, it's how you creep around that in terms of your flight test profile, so that you encounter the vortex ring state if it's there under situation under conditions which you can control. And if your engineers have done their homework, then hopefully they've got some semblance of a boundary mapped out for you, which describes where they think at least the problems are going to start to manifest themselves.
Okay.
What I see with the density is we for flight test purposes, we go up at higher altitudes where the density is different, but to keep the disk loading right, then you might need to change the weight, right, or again work with the thrust. But we use altitude for safety, and then you compensate through other means. Yeah.
It's one of those VMCA cases right now that sometimes you gotta do it very light and low, but
Rick, you got a question?
Yeah, you kind of alluded there as the weight is a factor, and the difference may be in these configurations also that if you've got a fixed wing where it's tilted up, then as you increase thrust, you're effectively increasing weight because of the downwash on the wing. Is that taken into consideration anywhere?
It certainly should be if your design has a strong rotor wing interaction. Yeah.
Okay, and the corollary to that is if you've got a tilt wing and now you've got basically a blown wing, as you increase thrust, you're increasing the flow across the wing. Would that also be maybe, and it also might get into where you're saying it may funnel the vortex away from the prop or the rotor. Is that considered anywhere?
Certainly, that's a very important consideration as well, and that's where the devil's very much in the detail. So it's how your rotor is actually oriented with respect to the wing, where the wake from the rotor actually goes as it passes over through the wing, or the wing passes through the wake. Put it that way is normally the situation. Things can become incredibly complicated once you start talking about wing rotor interactions.
Yeah. Thanks.
Okay. So, Dr. Brown, this has been awesome. This is just the kind of thing that has, sort of been in the background for all of us, and we're glad that we got a chance to start this conversation. What I'm going to do is we're going to circulate this. We have almost 300 members in the council. So after everybody gets a chance to review this, and then I'm going to ask for questions, and then I'm going to ask to bring you back for a round 2, and
Absolutely.
Q&A and whatever, more research and so forth. This is fantastic.
I'll do less talking and then let other folk chime in. It's been an absolute pleasure to speak to you all, and thanks for inviting me. And I look forward to round 2.
Right. Yeah. I mean, our purpose is to be the best flight testers we can, and being informed and being aware of where the weak points are and what's coming our way is what we're looking for. And so you really helped us identify some of those spots. So more to come.
I think there's huge potential, and I think where engineers and pilots and designers and regulators together to further the industry, that's where we should be operating, right?
Okay, outstanding. Well, thank you very much. Let's go ahead and officially close the recording, and